Video we're going to review our unit circle and kind of look at how it helps us very easily evaluate, say, sines, cosines, and tangents and their reciprocal functions at any angle. So really quickly here, we're going to go ahead and imagine we have an angle in standard position in the xy coordinate plane. So starting on the positive x-axis and terminating in one of these quadrants here. Here's our angle theta. When we talk about our definitions of the trig functions, we often represent these in terms of some point xy on the terminal side, okay, and it intersecting a circle of radius r here. And so you can see that it's hitting our circle of radius r. Well, if this is our unit circle, well, then we know that our radius has a length of 1. So what that does for us is it kind of takes this definition of sine, which is y over r, and makes it y over 1. Basically, in other words, our y value here on this point gives us the sine value of this angle. And likewise, we know our cosine value, which is x over r. Well, in the unit circle becomes x over 1, and here we have our x value. So again, with a unit circle, our cosine value is our x value here. Every point on the exterior is cosine theta and sine of theta. So one thing that is very helpful to do is oftentimes just kind of sketching out your unit circle on your paper, and you might say, well, that would take a long time to do, but in reality there are really only 7 angles we tend to represent here between 0 and 2 pi, and the first 4 are our quadrantal angles. Because the radius of this unit circle is 1, then we know these 4 points here are just 1 unit away from the origin. Okay. The other 3 angles we tend to represent are 30, 45, and 60, and I kind of exaggerated here, but all of these ordered pairs, recall, they all have ratios that are all over 2. So these are all over 2. Your x ratio and your y ratio, or your cosine ratio and your sine ratio. And as far as the tops go, there was a pattern. We said 1, root 2, root 3 on the left, and then 1, root 2, root 3. While we're at it, it's worth kind of maybe writing down our tangent values here, because those are worth noting. But our tangent of 45, remember that our tangent value of anything is y over x. So in the case of our unit circle, we're kind of saying our sine value, right, divided by our cosine value. So if we were to take our y over our x at a 45 here, we get root 2 over 2 divided by root 2 over 2. That means our tangent value is 1. Up at a 60, root 3 over 2, which is our y value, divided by a half, that'd be the same as root 3 over 2 times 2 over 1. So we get root 3. Okay, root 3 over 1, or root 3. And then down here at 30, this is just the reciprocal of root 3, so 1 over root 3, which rationalizes out to be root 3 over 3. So this unit circle, all I'm saying is you want to be able to recreate this on your paper at any time, and we actually have used a trick, the left-hand trick, to at least help us evaluate for 30s, 45s, and 60s. So how would that apply maybe in these situations here? Well, you know, if we want to find the exact value of trig functions at convenient angles here, we're just going to use our unit circle. So how about letter A on number 2 here? A couple things. We want to find the cosine of 210. The very first thing we want to acknowledge is that it's easier to use reference angles a lot of the time. So if we were to sketch a 210, what would that look like? It would go counterclockwise, terminate in the 3rd quadrant, and here would be our 210. The idea, though, is that it's making an angle with the x-axis here that would be, in this case, a 30-degree angle. So the idea is going to be that instead of doing cosine 210, we're just going to do the cosine of 30. And as a follow-up, we also have to check to see would this be positive or negative. And so because we're finding tangent of an angle that terminates in the 3rd quadrant, we're finding cosine of an angle that terminates in the 3rd quadrant, our tangent is what is positive in the 3rd quadrant. So we know that our cosine value here has to be negative. And as far as cosine of 30 goes, well, we'll just go look on our unit circle here. Cosine of 30 is just this root 3 over 2. And so we'll just write negative root 3 over 2. Okay. Head next door, you know, this cosecant of a negative 135. Again, I'm keen on using reference angles here. This would go clockwise, and a negative 135 would put us right around in this area here. So as far as what I want to do, I want to use this angle it's making with the x-axis here, and I observe that this is a 45-degree angle here. So we're going to rewrite this as, instead of the cosecant of 135, we'll just do the cosecant of 45. Okay. And as far as would it be positive or negative, well, this also terminates in the 3rd quadrant. And the only thing positive down here is our tangent function and its reciprocal cotangent. So this cosecant is going to have to be negative. And as far as what our cosecant of a 45 is, well, we'll just go take a look at our sine value and flip it over. So if our sine value to 45 is root 2 over 2, you guys, this is negative 2 over root 2. And we would have to rationalize this into negative 2 root 2 over 2, which becomes our negative root 2. And then last but not least, this 3 pi halves here. Where would that be? Well, this is actually interesting because if we know pi is 180, half pi is a 90, 3 pi halves, well, that's down here at 270. So 3 pi halves is down here. Well, how are we going to do this? Because, you know, our angle is this angle right here. Well, the thing is that this is a quadrantal angle. And so when we look at the outside of the circle here, we're really just kind of looking at this ordered pair and saying, well, I want the tangent. The tangent would have to be y over x. And in this case, down at that point, it'd be negative 1 over 0, where we would have to say that this is undefined. Okay. So also, along with using our unit circle, I want to know that you guys can reasonably find the angles that give you sines, cosines, and tangents of these ratios that occur on the outside of the unit circle. So looking at, say, these 3, 4, and 5 here, I say, hey, do me a favor, find the angle on the given interval that makes this statement true here. So, you know, I guess on number 3 here, I'm asking, what angle is it that when I take the sine of it, I get root 3 over 2? But I'm also throwing in the fact that our angle here is between pi halves and pi. So if we were to look at this objectively here, we would say our angle starts in the positive x-axis and is in the second quadrant somewhere. This is between pi halves, okay, pi halves and pi. The question is, so what is this angle right here? And what we were told to begin with is that the sine of this angle is root 3 over 2. So, you know, the real question becomes like, really, what kind of an angle are you making with the x-axis here? Because that's going to give us insight into what this standard position angle is. And if sine is root 3 over 2, you know, looking at this unit circle we sketched over here, sine is root 3 over 2 when it makes a 60 with the x-axis. So that means that this has to be making a 60 with the x-axis. And because it's terminating in the second quadrant, this angle has to be 180 minus a 60 right here. This would have to be a 120-degree angle. Or if we're doing this in radians, 2/3 pi or 60-degree rotations, okay? So we're looking for what angle causes this to be true, but we're restricted to a particular quadrant. And you can see that our unit circle still comes in handy because we have to know what kind of an angle we're making with the x-axis if sine is root 3 over 2. So how about number 4 here? You know, we take a look at this. We're told that the angle is between 3 pi halves and 2 pi. So our angle looks like this. Positive x-axis terminates down here and wraps around, okay? The question really becomes this then. If this is our angle theta, what is it? And we know it's between 270 and 360, but what's going to help us out here is if we know this angle it makes with the x-axis. And again, if we know tangents equal to -1 or even +1, the only time this ever happens is if this angle is making a 45-degree angle with the x-axis or has a 45-degree reference angle. So if that's 45, we know one full rotation is 360. This angle in standard position between 270 and 360 must be 360 minus this 45 here must be a 315. Okay, so in this case we say theta would have to be equal to 315 degrees, or if we're doing radians here, that'd be 7 pi 4th rotations. Okay, and then just for this last one here, let's go check out, you know, what would this angle have to be if we took the secant of it and we got negative root 2. Okay, well, what we're told is this angle occurs or terminates in the third quadrant here between pi and 3 pi halves. So here's pi, here's 3 pi halves. So we know our angle is somewhere between 180 and 270, and it looks like this. We were told to begin with that the secant of this angle is negative root 2, and the idea would be this. Well, that doesn't help me out with the unit circle very much, but I know that if I have a secant of negative root 2 or negative root 2 over 1, then my cosine would be negative 1 over root 2, which upon rationalizing this, right, we get negative root 2 over 2, and this kind of is our tip-off here that, well, if cosine's coming out to be a negative root 2 over 2, well, guys, this must be making a 45 with the x-axis right here, so this is 45 degrees. So, you know, putting this into perspective, then what would this have to be here as far as the standard position angle goes? It'd be 180 plus 45, that'd be 225 degrees here would be our theta. Or we could say 5 pi 4ths if we're doing this in radians. So it's key to know your unit circle, key to be able to sketch this on your paper and use it along with reference angles to evaluate for angles and ratios.